Hello and welcome to my talk. Can people hear me? I may not manage to stay at a proper distance to this mic, so apologies in advance. Okay, this talk will be about proof assistance in general and a particularly used proof assistant in particular. We have proved some technical results in the paper about definitions in higher order logic, abbreviated HOL. I'm going to spend a lot of this talk on motivating this line of work and describing the general ideas. And therefore, I apologize to the experts. So I'll be happy to give a separate private talk to anybody who wants to learn more about this. All right, so this is this is joint work with my colleague, my younger colleague, Andrei Kunčar from Munich. And as I said, this talk is about proof assistants. For anybody who's not familiar with what they are software tools for specifying mathematical concepts and stating and proving properties about them. And the distinguishing features of this particular formal method is their wide expressiveness. So essentially, you can model anything, semantics of programming languages and so on. Of course, you don't have full automation, but the wide expressiveness is the main characteristic of proof assistants. And they are increasingly used to offer high degree of assurance for, let's say, mathematical theorems, pieces of mathematics, or pieces of software and hardware. And thanks to improvements in automation, they are becoming more and more used, and hopefully, in the end, they will end up guarding the whole galaxy or the whole universe. But the question I want to address today is an ancient question that is particularly timely today. Who's guarding the guardians? So if we have a look at these grand guardians of the galaxy, they are only software in the end. So they are unverified software, most of them. Therefore, they exhibit bugs here and then. So we can very roughly distinguish between several components. We have the logical core, or the inference engine and definitional engine and so on. So this is essentially the implementation of the logic. Then we have a tool layer. It may, let's say, in a very generalized understanding of the word. So it may include a tool for a tactic language and so on. Typically, the tool layer involves the logical core. And, of course, a user interface, which is very important. It can be graphical or command line. So at all these layers, it is normal and acceptable to have bugs. Any system that is trying to evolve will have to do this through bugs. So bugs are OK. At the tool layer, most of the times, they could be annoying, but they would probably be harmless in the sense that they would not prove things that are not provable in a reasonable system. At the logical core, we also have bugs because this is a piece of software. And this is also OK. Typically, an implementation bug can be easily fixed if you have a nice specification of the logic. But you also have what I call logical flaws here. We can also read this as design flaws. And this is not so OK because this can be something very deep in the logic, or can be something more shallow, but nevertheless, it's going to be harder to fix because it is a property that affects the system globally. So it's not about just enabling a particular test and so on. OK. Right. So as a consequence of me editing the slides at the very last moment, something is missing. So what is missing is the notion that we have a distinction between, this is an important distinction that I want to make today. between an implementation bug and a logical flaw. So an example of an implementation bug, let's say a side condition is not implemented correctly, as prescribed by the logical system. On the other hand, a logical flaw can be something conceptually wrong in the inference system or in the termination or guardedness checker, conceptually, and in the pen and paper development of the system. And ideally, one would expect that mature and heavily used and heavily tested proof assistants do not exhibit logical flaws, at least. But unfortunately, this is not the case, and it happens quite often that proof assistants exhibit proofs of false. These are two particularly famous, let's say, examples that have affected recently probably the two most popular or user-populated proof assistants in use. This was in 2013, a bug discovered in the termination checker that allowed of COC that allowed a proof of false from that allowed the inconsistency emerging from a widely used axiom, proposition extensionality. And 1 year later, there was a problem with the definition, with circularity through a type definition in Isabelle that allowed an unconditional proof of false. And these are, I will not have time to argue about this, but these are conceptual flaws. They are not just implementation bugs. So they are about designing the definitional mechanisms. And I have to apologize to the other proof assistants for omitting them. They have some very nice story to tell. So absolutely. But the point is that even well-maintained and heavily used proof assistants are not immune to this virus, to proofs of false given by conceptual logical flaws. Of course, the immediate question is, does this endanger the whole galaxy? Does this endanger the kind of properties that have been proved with the proof assistants? Let's say the flawed version. And the answer is definitely no. There are several reasons for this. One of the reasons is essentially what I showed before, is the construction of a proof assistant that essentially isolates or quarantines the problem by its very nature. Other answers are the fact that actually such flaws have been discovered, have been fixed, and this has not affected the developments in a major way. So what was previously proved with a proof assistant, including software, hardware, big proofs, and so on, have been recovered quite easily, as far as I know. Another reason that is often invoked is that honest users would not take advantage of a proof of false, even if it's there in front of them. A proof of false, of course, being something extremely useful because of the explosion property, but it's not something that waits there on a plate for a malicious user to pick. Obviously, we're not talking proof assistant users are not these malicious users from the security adversarial models. But on the other hand, the tools are. So we have automatic tools that, if they are good, they should be able to pick up such, not necessarily to pick a proof of false, but be able to exploit the nature of the problem that led to a proof of false in order to prove other things. So the reason why those bugs that I have shown you have not been discovered for 17 years in Isabelle and Koch, and similar other problems in other problems, was because we didn't have strong enough tools to take advantage of those. Maybe not even discovering the inconsistency, but being able to prove silly things. So tools are there, and even non-malicious users like to have automation. Another problem, let's say a political problem, is the fact that because of the high degree of trust, proof assistants are now considered by certification agencies and so on. And there was a very interesting problem reported recently by an Isabelle Power user who had a lengthy discussion with non-experts, representatives of certification agencies about a recently discovered proof of false that was about to be fixed. So these are strong incentives to try to avoid such problems. So this is a fact. We could identify, based on several examples, that the strong vulnerability place is the definitional mechanism, as opposed to the logical inference, but I don't have a really strong evidence for this. Nevertheless, the definitional mechanism is one of the vulnerabilities, and in order to understand why this is, we have to look a little bit at, we have to take an evolutionary approach, an evolutionary take. Going back to let's say, to the early days in theorem proving, we had, or we still have this, but this doesn't really affect proof assistance anymore, so to a large scale. We had two different approaches. There's the axiomatic approach and the definitional approach. In the axiomatic approach, you model the problem by a set of axioms that you find appropriate, some ad hoc axioms, and then you prove the desirable properties. And the definitional approach forces you to use a fixed logic and define your concepts from the available definitional mechanism. Obviously, the definitional approach is much safer. And the essence of definitions, the reason why they are better than arbitrary axioms, is that in principle at least, they or their effect can be compiled away without losing probability, without losing probability. Okay, but as I said, definitions are also very inconvenient, as opposed to just stating any axioms that you may find suitable. Therefore, most successful proof assistants are applying the following strategy. They enforce the definitional approach for safety, but they strive to make definitions as expressive as possible in order to allow the users to write. For instance, most proof assistants can write recursive definitions, such as this simple definition of the factorial. Obviously, there is a quest and a competition between proof assistants to accept more definitions without bugging the users with requests for justifications and so on. So pretty much all mainstream proof assistants can accept fancy, much fancier definitions than the factorial. This is an example in my favorite proof assistant. This is a definition of the Collatz conjecture, for instance. It takes a natural number and returns a lazy list that is given by the Collatz sequence from that number. And it is a combination, a mixture of recursion and co-recursion, and so on. So this is quite fancy. This is cons on lazy lists. And you basically have a recursion call, a co-recursion call, and overall, they work fine. They form a well-defined, a well-formed definition. But of course, getting such checks wrong can be devastating and can lead to inconsistencies. So different proof assistants, they have different strategies for addressing this. But the idea remains the same. There is this quest for expressiveness, and therefore, I would say that proofs of false or inconsistencies are a consequence, a natural consequence of the definitional ambition of a proof assistant. Okay. So what can be done about this? I would argue that a reasonable measure here would be to formalize and verify not the implementation of the proof assistant. This is especially heavily used proof assistant with many users evolve too fast, although some people have managed to do this for some smaller provers, but have a precise specification of a detailed specification of the precise logical system. This also evolves, but not so fast. And one should pay particular attention to the definitional mechanisms. And this should be, in an ideal world, it should be part of the manual, of the documentation manual of a proof assistant. What properties should be proved? Well, of course, those deemed important by the community of designers, users, and developers. Obviously, consistency should be on this list, but you may want to consider stronger properties. Okay, so let's have a look at the definitional ambitions of proof assistants. We can split them roughly in two categories. There are some provers that are in neither category or in between and so on. But we have type theory-based provers such as Agda, Hock, Lean, Makita. And they have recursion, sometimes co-recursion as well, built in for types and for functions. For instance, you can define I'm using ML-like notation here. You can define the data type of lists as a nil and a const. So this is a recursive definition, and you can define things like length. So you have recursive type definitions and recursive functions definitions built in the logic. Consistency is ensured by some positivity checks in the type definitions or guardedness checks, or more recently, type-based analysis. Of course, the systems are quite complicated and the specification mechanisms are quite fancy. So there's the danger that if the analysis, typically a pen and paper proof of strong normalization, is flawed, you end up with a proof of false. On the other hand, you have the safer provers, the HOL family, the higher order logic, that sacrifice expressiveness, sacrifice a lot of expressiveness. They sacrifice dependent type, by the way. So this is a big loss. Not all of them. PVS has dependent types as well, but most of them. And there is a different approach to the definitional, to the recursive definitions. All recursion is compiled away. So it's removed, is reduced to non-recursive definitions. And for instance, you have a definition of a data type, and this is actually the data type of list is constructed as an initial algebra of a functor and so on. So we don't worry about consistency through recursion. But how about the non-recursive definitions? What do we know about them? So basically, we are left with only these safer non-recursive definitions. And what we know about them at a closer look is that they are, in some cases, neither non-recursive, and in some cases, they are nor definitions. So this is the current situation. Let's say with Isabelle HOL, you don't have a complete removal of recursiveness, and in general, in HOL, type definitions cannot be seen or cannot be immediately seen as definitions. And this is where our work started, with detecting that my co-author had detected that one of the proofs of false in Isabelle in 2015, and we started working on not only fixing that problem, but also proving that the bits and pieces of recursion there that have caused the problem are okay. How am I doing on time?
Yeah, 2 minutes, 4 minutes.
4 minutes? Okay. Okay, so apparently I have hijacked this talk for a general discussion of the proof assistance. Essentially, what we have done, we have shown that definitions definitions in HOL behave like definitions. This is essentially our result. And let me very quickly show you the logic that we're talking about. This is higher order logic, rank 1 polymorphic classical higher order logic with choice and infinity. So this is essentially simply typed under calculus with polymorphism added as a top level notation. And we have two primitives, minimalistic set of primitives, equality and Hilbert choice, and everything is defined from them. We have one of the most banal deduction systems from a set of definitions. We can deduce various things. We have introduction and elimination rules, and for the derived connectives, like for all, we have the expected rules and so on. So what's the problem with type definitions? Type definitions introduce isomorphic copies of a subset of a type, and the copies are required to be non-empty, and there are two isomorphisms that are introduced. So essentially, a type def is an axiom that looks like this. It states the existence of some isomorphisms when introducing a new type by carving it out from an existing type. And the requirement is to prove non-emptiness of the predicate, because a main design decision in HOL is that it keeps its types non-empty. Isabelle HOL is definitionally more ambitious, so it allows ad hoc overloading. The constants introduced are not required to be fresh, but you can define instances of those constants. And this enables a very nice feature, verified Haskell-style type classes. Okay, so this was a very quick introduction. We have a form of recursion because the overloading can be recursive. And there are some measures that have been taken but have not been proven correct. And actually some problems have been discovered. We have extended the proof of consistency from HOL to Isabelle HOL, the classic proof by Andrew Pitts. And there was an incentive to focus on a more syntactic version. This is what we did. We have expanded the definitions in the richer logic, but have complicated the logic in order to get rid of the definitions. The problem with this is that precisely it. So we have gotten rid of the definitions, but have complicated the logic. And the result that we have in this paper, you are welcome to read our paper and to contact me with questions. The result is a better encoding that really compiles away the definitions in higher order logic and ensures conservativity. Because I have hijacked my own talk, I will not have time to go through the description of this encoding. As I said, so the result can be found in the paper. And let me just conclude with some related work and with an invitation to keep a closer eye on our proof assistants so that they don't get, the definitions they don't get too expressive. Okay. Thank you very much. So this concludes.
Any questions, comments?
So, I wonder if the user is not so nice, then maybe this problem gets harder, right? I mean, for example, if you just have a printing mechanism which prints true for false and false for true, then it doesn't really help if the logic is consistent, right?
Right. Yeah. So and you have things like Pollack inconsistency
Exactly.
and so on, which are real problems. But yeah, so this assumes an adversarial user. Mm-hmm. But these kind of problems, these kind of tricks, they don't have a long life, especially when you upload the proofs in public repositories and so on. So I would say that these are shallow problems that are easy to solve. Okay. Whereas a deeper logical flaw is really problematic and can take years.
I'm sure the Russian mafia is pleased to hear this. Okay, thank you very much.